on Friday, can I come to office hours and have you teach the thing I didn't attend class for free with your time? I'm like, no, I'm not going to do that. So we were talking about vibrational spectroscopy on Wednesday, and the idea behind vibrational spectroscopy is that we use it to get structural information, right? And the reason we can do that is that bonds vibrate, they move at a certain frequency. It's a physical movement, right? And that's a harmonic oscillator. And that oscillation is based on the force of the spring, if you will, and the masses attached to it. And that's why a carbonyl group, like a C-double-bond-O CO bond, like bends, like folds at a different frequency than a, switching out that oxygen, that single bond oxygen with another carbon, right? The masses have changed, the bond strength has changed. So we can use those frequencies to get information, right? So I'm going to draw cocaine. You have it in your notes. Cocaine is a 7-membered ring. I'm going to try to draw. I feel like that's too many carbons, but it's not. Okay. I mean, you've seen me draw hexagons. You guys know that my organic drawing skills are garbage. What do y'all know about cocaine chemically? Don't tell me it's a hell of a drug. All right. This is its structure, right? Looking at cocaine, just as a molecule, we're chemists. What stands out to you? What are some things that stand out to you about this molecule that might be interesting or give us clues if we were to sort of take an IR spectrum of it, right? What would be some clues that would tell us what kind of molecule we have? What are some things that stand out to you just looking at the structure of cocaine? Carbonyl. It's got a couple CO double bonds, right? Those are interesting. Anything else?
A benzene ring.
Yeah, there's a phenyl ring, right? Anything else?
And a bicyclic group.
Yep. And an amine, right? Amines are what kind of molecule? Do they have acid-base characteristics? They do. Jackson says they do. He's right. Yeah, right? So there are amine groups. There's this bicyclic group, right? Absolutely. Or a bicycle. Bicyclic. There's carbonyl groups. There's phenyl groups. All right, there's this group here. I forgot what that's called. That functional group. I can't remember. I took organic chemistry a long time ago, and I didn't just delete that file. I threw out that whole mental hard drive, right? Once I got my A in it, I was like, I'm done. So you can probably guess that if you had a molecule other than cocaine that had similar functional groups, you may have a pretty similar IR spectrum, right? And that's true. IR spectra are not 100% definitive. You certainly couldn't convict somebody on an IR spectrum, right? But we can use these to confirm what we have, right? So for example, let's say that Rebecca gets pulled over. She's driving erratically. She's in 2.5 lanes. I don't know how you would do that in a car. She's like totally drift racing, right? And they pull her over and she's got this mysterious bag of white powder in her glove box. And she's like, I don't know what that is, right? They'll actually take it and do FTIR analysis. And if it doesn't have the amine group, right, with the wave, it's right about 3,300 wave numbers, right? Or certain other functional groups, then they know it's not cocaine. It may be something else, right? But it's certainly a way of excluding what it is. You couldn't convict someone. Now, if it had all the functional groups you're looking for, then you're in trouble, right? Because then they'll do more tests. The other thing about FTIR is IR is a mature technique. It's well characterized. Sorry. It's Good Friday if you celebrate that. I guess if you're celebrating Good Friday, you're not really celebrating Good Friday, right? If you're religious, if you're Christian and it's Good Friday, then it's not like a day where you're like, woo, crucifixion. But still, so if you're observing Good Friday today, I'm going to try to make it, I'm going to try to make it a Good Friday and at least have better handwriting, I promise. All right, it's well characterized. And why that's important is that you can match your compound to a spectral library. In other words, there are so many IR spectra that exist already for so many compounds. The structure of cocaine is a good example. If you have the IR spectrum of cocaine by itself, you can, as a student, like put on your thinking cap and say, oh, okay, this is a CH stretch, and this is C double bond O stretches, okay, and try to piece the molecule together. But if you'll notice in your notes, between about 1400 and 800 wave numbers is a very dense number of peaks. We call that the fingerprint region. So between about 600 and about 1500 wave numbers, there are many peaks, and we call that the fingerprint region because we actually use algorithms to match that fingerprint region for my compound. So now, while you can't use IR spectra, I should have pasted this in the notes for drawing on it, that's all right. If I draw out the transmission spectrum versus a function of frequency, this is nu with a tilde on it, right? Nu with a tilde is frequency divided by the speed of light. It has units of wave numbers. And it goes in increasing wavelength or decreasing energy. So 4,000 wave numbers is the high end, about 600 or so is the low end of the spectrum. And there'll be, for example, like an NH peak around 1,500. You probably remember some of this stuff, right? Right around 3,000, you've got alkane and alkene peaks, and then you've got like, C double bond O peaks are over here somewhere. And then there's this region of many, many peaks called the fingerprint region. And just like we use little swirls and patterns in your fingerprints to identify that you indeed are a criminal, or you are indeed who you say you are, right? We can use the complexity of that fingerprint region to match spectra. And now you're like, oh, I think I've got cocaine, right, in this bag that Rebecca had. Sorry, Rebecca. And this region here is matched to a spectral library, right? These are things that you have to buy, like libraries aren't cheap. But the nice thing is, you're like, what is this mysterious compound I have? FTIR may be able to match it through algorithms. So we don't really use it. We use it still to confirm functional groups. You did it in organic chemistry, right? Correct? Do you remember doing this? Good. Okay. The next thing I want to talk about actually, while we're talking about cocaine, because cocaine's an interesting molecule and it's Good Friday. Do you mind if I divert a little bit and talk about cocaine chemistry? Okay. If you're like, no, I'm paying for instrumental analysis, let's talk about cocaine instead for a minute. Cocaine is the really important thing is this acid group right here. Okay. I'm going to copy my cocaine molecule. Bring it down here. I brought my kids to this lecture once because they had like Good Friday off, and they got to come to the car to have lunch with my wife, and she was like, "How was Dad's lecture?" And they were like, "It was great. We learned about cocaine." And I was like, "Well, my 7-year-old had a good day." She's a biochemistry major now, so maybe this is influential to her. Cocaine's acid group is kind of interesting. This is actually kind of the magic. It's an amine, right? So if it, in its current state, is it an acid or a base, looking at its molecule? It's a base, right? I can, of course, protonate it if I want to, right? So cocaine, HCl, is the protonated version. This is a white powder, often stored in kilogram bags, right? So when you see in a movie, I'm assuming most of you haven't seen actual cocaine in the wild. You shouldn't have at this point.
Dr. Pappas,
Yes.
Jordan asked if you could please let him in.
Maybe. Don't let him in? It's me $5 to get in. I should do that. Like, I'm just kidding. Do not report me. All right. Actually, you should be like, if a student emails you and is like, hey, tell Dr. Pappas to let me in, you should charge them $5 to tell me that. you can certainly make money off of this endeavor. I don't need to. All right. So cocaine, for those of you that are just joining in, we're talking about cocaine today because it's interesting. Cocaine, HCl, is the protonated version that when you watch a movie with a bunch of drug lords from South America and they've got a speedboat, right, and they've got keys, right, kilos of cocaine, kilograms of it, it's in this form. It's stable for storage. It doesn't decompose. It's not very bioactive. What does cocaine do to you, like chemically, when you use it? Anybody know? What was that? It's a stimulant, but what part of your brain does it stimulate? The dopamine receptors. So what does dopamine do? It makes you happy, right? Dopamine actually doesn't make you happy. Dopamine is actually the anticipation of happiness. Anyone here have a new girlfriend or boyfriend or whatever? It's relatively new? Or are you all in like either single or in a relationship full of malaise and stagnant air? So you've got a new significant other? It's exciting, right? They text you, you're like, oh, they text me, right? I wonder what it says. Did they miss me? It's been 2 hours. Whereas like 30 years from now, you're like, oh God, what do they want? Did I forget to take out the dog or whatever it is, right? I mean, I'm not there yet. I don't know if I'm going to be there. But I'm saying, when a relationship is new, it's pretty exciting, right? And you're anticipating seeing them. When you get dumped, anyone ever been dumped before? Not exciting. No one's raising their hand. It sucks, right? You don't want to eat or sleep. It's the dopamine withdrawal. That doesn't make it any better. Like, I'm sure. Like, in fact, if you're hanging out with your bro this weekend and he's mad because he got dumped and he's crying in his beer, don't be like, dude, it's just some dopamine withdrawal. Suck it up. It doesn't comfort them. Trust me, right? But cocaine stimulates your reward center and makes you feel amazing, right? I've never used cocaine. Right? Just want to make that very clear. I know my lectures seem like I'm probably on cocaine because I'm super amped up. I'm like this all the time, y'all. My poor family. I'm always amped up. All right. So it's not bioactive. The base form, however, is more bioavailable. When we say bioavailable, it means that your body can use it. You all have heard the term bioavailability before, correct? Anyone not heard it? Or not familiar with it? Well, I'll give you a brief example. Let's say that you're anemic and your doctor's like, you need more iron, right? Well, you can actually chew on fragments of a cast iron skillet, and aside from destroying your teeth and having a really exciting 24 hours, nothing will happen. Because metallic iron is kind of useless to you, right? You need iron 2+, what we call reduced iron, correct? Right? Not iron 3+. Your body doesn't really use that. It just turns it into iron 2+. So the bioavailability of metallic iron is very low, right? Lead is another good example. Lead as a metal is not that bioavailable. It's really when it becomes lead 2+ in your system and makes like organic lead compounds that's really toxic. So the base form of cocaine is more bioavailable. So you need to ship this stuff in an acid form because it won't decompose that way. But then you really want to, if you're trying to get really high, you want to convert the cocaine to the base because it's more intense. You can use less cocaine and get more high. Kind of a win-win from economics, right? So in the old way to do this was you would add either potassium hydroxide or sodium hydroxide, concentrated, to remove the base. So you would have cocaine that's acidified, you'd add hydroxide, and you get water, and then the base, what we call the free base, because it's free of the acid. However, you've got a ton of hydroxide excess. Just like we talked about, I'm going to tie this to fluorescence if I can get away with it. Just like we talked about derivatization, we had a molar excess of a reactive dye, right? When you want to add a fluorescent molecule to your anthracite to drive the reaction to the product side via Le Chatelier's principle. It is no different when you want to get really high. You add an excess of the base to drive the reaction to completion. I don't know about you, but do you all know, sort of the health effects of ingesting a concentrated hydroxide. It's not good. So you need to remove this. So step 1. Step 2, you extract the cocaine with ether. Just like organic chemistry, right? Agitate, you separate the phases, skim off the ether phase, which has your cocaine, and then ether is fairly volatile, so you just let the ether dry. Now, if you're a chemist, you would rotavap it, right? But if you're just a junkie, you don't have a rotavap at your house probably, unless you're really hardcore into cocaine. So you just let nature evaporate, right? Just let it, it's got a high vapor pressure. However, what do you know about ethers? They're really flammable, right? They're explosive, in fact. Have y'all ever heard of a comedian named Richard Pryor? Who has? It's hilarious. Don't watch this from your parents, right? Richard Pryor is a comedian from the 70s and early 80s. He was in some movies too, but he's incredibly off color. I'll just say that. He's very raunchy. And he almost died in an ether fire while freebasing. This is like a big deal. It was like the first time the public had really learned about things like freebasing. If you're snorting cocaine, like frat boy style, right? So you're snorting the acidified version of it, and so some of it converts to base in your bloodstream, and then you get high. If that's not cutting it for you anymore, like if you've been snorting cocaine for a while, and you're like, man, I just really wish I could get high faster and more intense, right? Like my tolerance is built up. Then you're going to freebase, and so you can buy sodium hydroxide, it's solid, it's pretty cheap, and then you get some ether. Now, if you start buying ether in quantities, you get a visit from the FBI nowadays, right? Because they want to know what you're doing with it. But you buy some ether, you get hold of it. I mean, you're already buying cocaine illegally, so I don't think ether is a big concern, right? And you extract the cocaine and you let the ether dry. Well, if you're already freebasing cocaine, I don't think you're a patient person. You know what I'm saying? So he really was like, well, that looks dry enough. I'm just gonna light my freebase. So after you extract it, you heat it up and smoke the vapor. So you inhale the vapor. You cannot smoke the acidified version. It's not thermally labile, because it falls apart at lower temperatures in the base one. The base one can withstand higher temperature in the gas phase. So you make your cocaine basic for 2 reasons. One, it is uptaken into your body faster, so the high is more intense. And then 2, you can smoke it, because if you have to deliver something to somebody, the best way to do it is through inhalation, correct? Why is it better to inhale versus ingest? In general, not just drug use.
Hits the bloodstream faster.
Hits the bloodstream faster because you've got these sacs in your chest, right? Your lungs are basically just sacs to hold gas, right? And they're covered with blood vessels so that you can transport a large amount of, from a mole standpoint, not mass, but from a mole standpoint, you move more moles of material through your lungs than any other process of your body, right? Just think about that, right? And inhalation, exhalation is a ton of, well, not a literal ton in mass, but a great number of molecules, right? So if you can inhale a drug, this is why we deliver albuterol to asthma patients instead of injecting it, because they're dying because they can't breathe. You need to get it there fast, right? If you could make glucose vaporize and take it into the lungs, then you'd have a mechanism to stop someone in a diabetic shock, right? A student of mine last year actually tried to see, he asked me if he could make a vape of like glucose. And I was like, no, because the sugar falls apart at those temperatures. So you heat and smoke your freebase, but the problem with that is it's explosive. And so Richard Pryor was an impatient person and was like, well, that looks dry enough. Lit his powdered freebase cocaine that was still wet with ether, caught on fire. There's more ether all around him because you've got a lab at that point. And he actually burnt to a crisp. And he was like really, 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 there was question about whether he'd be like permanently disfigured or not. So, you know, your typical freebaser was like, I don't want to deal with the hassle and the danger of freebasing. So maybe there's another way. Which brings us to crack. This is the part of my lecture that my children love the most. They're so happy to tell my wife, like, Dad taught us how to make crack, Mom. And I was like, well, to be fair. Crack cocaine, what do y'all know about crack cocaine in general? When I say crack cocaine, what do you think? Systemic devastation of urban communities? Yes, right? Crack cocaine has been a blight in our country on poor people. And I'm going to tell you this, there's a little bit of racial tinge to this too, right? Because a lot of white people were like, well, it's not crack, it's people that use it. But now that poor white people are hooked on opioids, opioids are a pandemic, a national health crisis, right? Like the language used to describe the exact same thing is very interesting, right? It's like how they describe Meghan Markle and Kate Middleton in the news, right? One is a hero for eating avocados, and one is a colonialist witch for eating avocados. So there you go. So crack cocaine is a big deal, right? It's a huge problem. So crack cocaine is kind of the same. You still need a base. So what we do instead, I say we, I don't actually do this, right? It's like the royal we, is that you've got this, your drug smuggling boat brings you the cocaine. And instead of a strong base, we just use a weak base. Anyone recognize this base? It's baking soda. If I buy a 50-gallon drum of ether, the FBI or DEA will come to my house and search it because I'm clearly doing something bad. I can go to Costco after class and buy 1,000 pounds of baking soda, and someone's going to go, man, he must have a lot of stuff to clean, right? No one ever questions it. How much baking soda is at your house? Not your house because you're college students, but your parents' house because they clean things, right? So you get cocaine-free base. So that's good if you're trying to do that. And some leftover salt and leftover or excess base. This makes a solid, what we would call a rock. And the reason it's called crack is there's water still. As you smoke the crack, sorry, I promised better writing today. All right. When you heat up a crack rock to smoke it, to release the cocaine into the atmosphere so you can breathe it, the water vapor trapped in the rock expands and pops like Rice Krispies cereal. So it could have been snap or pop, but they chose crack. So it makes a crackling sound when you smoke it because of the water vapor escaping. In fact, if you're at a party and someone starts smoking some crack, you can totally be like, did you know that it's called crack because water vapor is escaping? You think it would ruin the party? I mean, maybe. I mean, I would argue the people that are doing crack are probably already ruining the party and their lives, right? All right. Why is this important? Why? Because it's chemistry. I like chemistry. You get the same free base, which gives you a more intense high. Crack is more addictive than snorting cocaine because the high is more intense. And because it's bioavailable, it's consumed faster. And so the high is over faster as well. The less available acid form takes longer to get into your system and therefore longer to get out of your system, right? It's like when you're really hungry and someone gives you something to eat, you eat it faster if you're really, really hungry, right? Maybe too fast even. So your body just consumes that, and then you're like, wow, I need more crack, right? You don't need specialty chemicals. All you need is to mix the baking soda and cocaine at the correct weight ratio that I am not going to tell you. But it's in a Master P song, if you really want to find out. It's a horrible misogynist song, but it's there. It's the gram ratio. My colleague in mechanical engineering told me about this. He's a huge hip-hop rap fan from his days, and he was like, oh yeah, there's a song about that. With the rate, and that's how I actually learned the weight ratio for making crack. Sentencing laws for crack, by the way, are totally racist and classist because you can have 12 times the amount of cocaine powder and have the same sentence as having that amount of crack, even though the cocaine powder makes a vast amount of crack compared to the amount of crack that you had, which is a set amount. If that makes sense, right? Why is that? Because powdered cocaine is a senator's son type of drug. I'm serious. I mean, it's a rich person's drug, and those people have influence, right? So there's a lot of racism involved in the sentencing of crack because, again, I can have a lot of this and then go to Costco and make a whole lot of crack cocaine. By the way, in case you're curious, crack cocaine does, the crystal, the solid crystal does stabilize the free base so you can make it, store it longer. It's an advantage of making crack. Again, don't make crack, please. I have to say this because you all watch Breaking Bad and idolize Walter White, right? I haven't seen the show because I feel like it's irresponsible. I do. I think actually it really portrays chemistry in a very negative light. You know, everyone knows what it was like. Every time I say I'm a chemist, everyone's like, do you enjoy Breaking Bad? Like, can you make meth? Yes, I can, but I don't want to show. Right? So anyway, that's my soapbox about crack. But just understand though that really it's kind of a horribly ingenious chemical process. I mean, you can make a much more addictive and reactive version just by adding baking soda, and there's no separation step involved. No chance that you're going to catch on fire, just the chance that you're going to end up having to prostitute yourself because you're addicted to this thing horribly, right? Which is awful. All right. Yes.
Did you say that, like, so say, like, it's like commercial or whatever, and you have the normal, I don't know, cocaine, I guess. Is this the NaCl and the H2O, are they still in, like, say you would go and buy some, I don't know, no, not like I would ever do that.
You mean like for research use or like on the street corner?
On a street corner.
So if I buy a crack rock versus the powdered cocaine, you mean?
Yes. Is the powdered one, does it still have like H2O and NaCl in it?
It has. So it is when you buy it so you go to your shady drug hookup spot and you buy cocaine HCl. It's cocaine. And your hydrochloric acid is added to make it a powdered form. So it's not, there's no hydrochloric acid in it necessarily. It's just been protonated. So the cocaine has been protonated. So there's chloride in there, and there's always sodium as a counter ion. But not at the concentrations that we're talking about for making crack. Crack has so much sodium bicarbonate in it that it solidifies into a crystal.
Okay, cool. Just curious.
Just for asking for a friend, I know. All right. Oddly enough, I think it's always Good Friday that I talk about cocaine. But, I mean, it's interesting. Now, maybe you're like, God, Dr. Paps, we have a test next Friday. This is going to be a test. Yes. Everything that comes out of my mouth is on a test, right? Colton and Michaela's relationship is on the test. You laugh, but I can totally work it into a question. I've done it before, right? So, switching back to spectroscopy, if I may. Let's say that you've got a bunch of cocaine. Let's say you've got a crack house that you live in, that you employ amateur chemists making crack, right? And really all they're doing is mixing baking soda, water, and cocaine. They also keep a pot, a lot of times, of just like disgusting items, like literally tar and dirt boiling at all times as a sludge, so that if they get raided, they can dump the cocaine in that boiling pot. It'll decompose, and you can never trace what it was because it's like a soup of like literally like roof shingles and things like that, right? So now we bust in and we want to test whether or not you've got cocaine, right, on you. And maybe it's crack, which has a lot of water in it, and you're like, if only I could measure this by infrared spectroscopy, right? If only. How? How do you measure a solid with infrared spectroscopy? Now, I would like you all to go back to organic chemistry. You're all several years younger, hopeful for the future, before organic chemistry ruined your lives. And you all took organic spectra. Of solids or of liquids? Liquids, right? Okay. So what did you do? You dissolved it in a solvent, and then what? Was there a cuvette? I'm not asking you because I don't know. This is one of those, professors ask different kinds of questions. There's a question where I want to see what you know, which is one of these. Then there are questions I truly want to know the answer to, and I don't know the answer. Then there's a question that I call them thought questions, where I don't know what the answer is, and I know you don't either, but I want to see what you do under a moment of panic, right? So this is more of a question of I know the answer. What is the sample holder, if you will, in a regular IR that you've done for liquids? Anybody remember? Thank you, Cormac. A salt plate. Cormac, you're my hero today. You have 2 salt plates. Why do we use salt plates? What's special about a salt? Besides the fact that it's solid. If it's a simple salt like potassium chloride, and you're talking about infrared spectroscopy, what part of the molecule are we fundamentally measuring in infrared spectroscopy? Like, what's going on? Are we moving electrons around? Are we ejecting protons from the nucleus? What are we doing? Bond distortion, right? Bond vibration. So in a simple salt, are there bonds? Nope. So it's transparent, okay? So there's a salt plate, and then we put a liquid film between them, right? And then you've got your I0, and you've got your transmitted intensity, and that gives you transmission, right? That gives you absorbance. So this is how we measure liquids. But how do you measure a solid? That's a little bit trickier, right? So for infrared spectroscopy, we use something called attenuated total reflectance. I need you guys to do a little bit of homework, not really homework, because I don't assign homework to this class. I need you to review Snell's law. I'm not going to do it. Well, do anyone remember, I'm not asking you to tell me what the actual law is, but what does Snell's law govern or describe? Somebody read his lab description in my class. Yes, it deals with diffraction, or refraction, rather, going from one refractive index to the other, right? So let's say I have, for example, a piece of diamond. Has a refractive index of about 1.55, one of the highest solids, highest transparent solids. It's what makes it shiny, because a diamond is it's colorless. It's only pretty because light goes in, and because the refractive index is high. So when light goes in, and it's in air, so the air refractive index, when you go from a high refractive index to a low refractive index, more often than not, you have internal reflection, right? In a diamond that you might be wearing on a ring or something like that, or your earrings or whatever, the way that it's cut is such that those random bounces, obviously some light escapes every time, right? And so it's cut so that the light comes in, the high refractive index of diamond makes it bounce around. That's the magic of diamonds. That's the sparkle that results in children who are 5 and 6 years old mining them for you. Don't you feel that now? And if you're like, but Dr. Pappas, my diamond's conflict free, it's because the kid who mined it is now 20, right? It's not really good for you. I have a whole diamond lecture we could talk about sometime. They're really awful. But we use them spectroscopically. We use lab-made diamonds. There are no children involved in this process, right? And so light goes in, and because you're going from a high refractive index of the diamond to a low refractive index of the air, the light bounces, the light bounces backwards. Sorry, deleted my drawing. Internal reflection. Okay, what's called total internal reflection. Do you guys remember talking about total internal reflection in Snell's law back in high school? You look really surprised when it's in high school. I guess I had a pretty kick-ass physics teacher. I don't know. My chemistry teacher in high school was abysmal. In fact, after I got my PhD, all I went to see my parents. and I drove to my high school. And you know, have you ever like had like a shower fight or a car fight where you have like a whole dialogue by yourself? Like you kind of come to the scenario. I had like this car fight where I was gonna bust in to my chemistry teacher's room and be like, "Miss Sadie, you're a fraud," and then look at the students and be like, "I have a doctorate, so I know," and then run out, right? Like, haha. And I got to the school, I signed in as a visitor. I'm like, "So what is Miss Sadie?" And they're like, "Oh, she retired." I'm like, "This is probably good," because I was gonna do something really stupid and catty. But I had a horrible teacher, but I guess a good physics teacher. Total internal reflection occurs when you are above the critical angle, right? Going from a high to a low medium. And so the light bounces back inward. Total internal reflection is how fiber optics work. The internet that you're using, Zoom family, to attend this lecture is because a laser beam is firing a pulse every 1 and not firing a pulse for every 0 and sending you a digital version of my lecture via total internal reflection, right? The brave women and men who came to class today, making eye contact with me, laughing at my crappy jokes, are getting it live, but you're getting a total internal reflection powered digital facsimile of me, okay? Not quite as great. We call it total internal reflection, but we lied to you because you were in high school or freshman chemistry, right? Total internal reflection is not total. I was to magnify this surface. So here's my diamond. Here's air. And here's my beam. I'm going to make my beam a little bit bigger. So my beam hits the surface and then internally reflects, like that. Okay. A small part of the light penetrates the surface. We call this an evanescent wave. So every time there's a little reflection at the surface here, there's a little bit of the wave. You can think about it this way. The physical boundary between the diamond and air interface is not the actual boundary of the wave. The wave extends slightly beyond that interface. A little bit. So why do I care? All right, so I've got a diamond piece of diamond. Just redrawing it for a second. And I've got my IR beam. And it bounces, I mean, like tens of thousands of times. In and then out. And every time there's a little tiny reflection, there's this evanescent wave on the surface. Okay, so the gist of it is that IR light sort of penetrates the interface a little bit and resides on the surface of that crystal. So now, let's say I take, change colors here. Let's say I take a crack rock and I put it on this crystal and I apply just a little bit of pressure, not a lot, just enough to keep it, contacting this, right? I can't take a crack rock and put it in the FTIR beam path. It's a solid, right? There'll be light scattering, all these kinds of problems that make Beer's law fail. So instead, and I'm going to just draw the surface larger here, I've got my crack, right? This is like, magnified. I've got my diamond and the crack sitting on it. And you can think about the light path that's kind of going like this, into the crystal, along the surface of this crack rock, and then back out. So the light samples the surface. Which is a huge deal. You're a forensic chemist, and they find a piece of flannel at a crime scene. Does it match the piece of flannel found on the body? You can look at like fiber, you can look at weave, but it may not be, right? You can slap that piece of flannel without any sample prep onto the IR, onto the attenuated total reflectance accessory, the ATR crystal, and get a spectrum for it. You have an opaque plastic. I wonder what it is. And I run a recycling plant. You put it on the ATR crystal and you identify it immediately. No sample prep within seconds. It takes you longer for your brain to comprehend what plastic it is and decide which bin to throw it in than it did to make the measurement. So this is a way of measuring solids with IR. It's used for drugs. You can take powdered cocaine and put it on there. You can do all kinds of things, right? If you can have a sample touch the crystal surface, you can measure it by IR now, right? Which is really handy because a lot of things that are interesting aren't in aqueous solution. Let's say, for example, anyone have a car that's a bit older and see your headlights are kind of turning yellowish, like they're kind of fogging, like the cover of it, right? You can, let's say that you're an auto part manufacturer and you claim now that you are making plastics that don't have that problem, right? Well, what you would do, you want to, of course, maybe not expose your car to light for 5 years to prove your point. You might accelerate the aging process. You can actually just take that piece of plastic, measure it with IR, and show the aging process, the breakdown of the polymer into other polymers, right? It's used in forensic chemistry. It's used in manufacturing all the time. Let's say you're putting a thin plastic coating. So anybody here like to drink carbonated beverages in cans? Could be beer, could be sodas. You're college students. How many of you all drink beer probably, right? Maybe not. You ever thought about the fact that you've got, like, especially with like sodas, you've got a fairly acidic solution sitting in a piece of aluminum? Well, there's actually a plastic as a polymer layer on the inside of the can to protect the metal from the actual acid that you're ingesting. A lot of cans, a lot of food cans are lined. You can even feel it, like on a soup can, there'll be like a lining, a polymer lining, right? You can't cut a piece of that polymer lining and stick it into the FCIR because the metal will block the beam, right? But you can cut that piece of metal off that can, slap the lining side down on the ATR, and get the spectrum. And maybe, just maybe, I mean, this happens. There are times where maybe you're in a canning company and your lining is failing, right? So I open my can of soup, and there's like bits of, huge bits of floating plastic sheeting in it, right? Not appetizing, correct? So you are now told, hey, we have like, $5 million of soup that are all being thrown out. We'd like no more of it to get wrecked. Find out what's going on with the polymer, right? And maybe it's an adhesion thing. Maybe the polymer's degrading. You would do all of this by ATR. Okay, it's a really useful technique. Now, the next thing I want to talk about, I feel like maybe you should all have taken some drugs today, maybe not cocaine, is Raman spectroscopy, because it's really weird. It was discovered by C.V. Raman, an Indian scientist, who was actually a physicist who was really into violin research, like how violins vibrate and transmit sound, and how can such a small object create so much volume, And then he found this thing kind of on accident and got a Nobel Prize for it, and it's named after him. So it's kind of cool. It's one of those science moments where he went like, that's weird, and then did some actual experiments, right? And got a Nobel Prize. So in Raman spectroscopy, it's vibrational spectroscopy. And it's a complement to IR. I was writing the wrong kind of complement. I was writing the your haircut looks good compliment instead of something that goes along with it. So it's a complement to IR. It gives you very similar information, not identical because the selection rules are different. It's a semi-quantized technique. We'll talk about why later. And it's the weakest optical effect. It's the weakest signal in spectroscopy. Any of you ever play Punch-Out on Nintendo? You have? So the very first person you fight is Blast Joe. It's been a long time. I can beat the first guy on Punch-Out. I cannot after that. My son's pretty good at Punch-Out. He beats the first guy like in 3 seconds probably, right? This is the Glass Joe, or the weakest character, if you will, of spectroscopy techniques. It's weak in that you don't get a large signal. And so because of that, when we talk about the instrumentation in this, you'll notice a lot of things we talked about earlier in the section of notes. We use a lot of the techniques because we are so starved for light in the Raman effect that its evolution into a useful technique was actually driven solely by instrumental analysis advances. So new types of detectors, new types of monochrometers, using lasers, for example. Nobody used Raman at all practically until lasers were invented. Like, it was discovered in 1929 or 1932, I don't remember exactly. And it wasn't until the late 60s that it was actually used by people in general. And for the longest time, it was only used by physical chemists living in their basement dungeons as like an esoteric technique. It wasn't until the mid-1990s when CCD detectors became common that you could actually acquire a spectrum and use it for analytical purposes. So it kind of became a big deal. What I'm going to say today is going to sound weird, but Raman spectroscopy basically is what's called inelastic scattering. So it's a light scattering technique. You have a molecule, right? And you have a photon, or photons, plural, of light that interact with it. Now, this photon does not match an energy transition. That's why I said it's semi-quantized. So the wavelength of my light actually doesn't matter. When we talked about absorbance and talked about fluorescence and talked about emission, I always said that the light being absorbed has to match the energy difference between two levels, correct? And it can't be less than or greater than. It has to be an exact match for that electron to move from one state to the other, correct? Because that state has a defined beginning and a defined end, the difference between them has to be known, right? So if I'm moving them exactly from one place to the other, I have to have that exact energy input, okay? In this case, we're not doing that. We don't care what the absorbance energy is. We're just interacting with it. And so an electron cloud around a molecule is an electric field, correct? And a photon is also an electric field. And they tend to repel each other, right? So what happens is you get scatter. And we talked about scatter already. We talked about it because it has that peanut-shaped distribution, right? That's why we measure fluorescence at 90 degrees. So light scatter just literally bounces off the molecule. Most of it is elastic. In other words, no energy is changed. So the wavelength of the scatter is the same. It's a beautiful day out today. What color is the sky going to be when we go outside and look at light again? Assuming there's no dust. What color is the sky? Blue. You ever wonder why? Rayleigh scatter, right? It's light scatter. This is what we're talking about. It's elastic scatter. So sunlight hits molecules in the atmosphere and scatters. Molecules will scatter light. And scattering actually has a wavelength dependence to it. So blue light scatters more efficiently than red light. If there is UV light on our planet, which there isn't really much of, and we were bees, we would say, no, the sky is ultraviolet, not blue, right? We would see a different color, right? The sky is blue because of elastic scatter, right? So light just gets, instead of being unidirectional toward the ground, gets scattered in different directions. And blue light scatters more than red light or green light. That's why we see the sky as blue. So when you're on a date, and your date's like, I ever wonder why the sky's blue? You go like, well, actually, and then tell them, and the date will go south, right? I was on a double date in college, and my girlfriend at the time and her best friend went out with my best friend, and the other girl went, isn't it weird that pickle smells so strongly? The correct answer is, I know, right? Conversation back to you now, right? Let's talk about you. And my best friend went, well, actually the vapor pressure of acetic acid, the date was over. You could just see, like, she was like, oh my God, are we going to the movies also? And I was like, shut up. We got in the car, I was like, dude, vapor pressure? That's date 10 material. Maybe date 20. You don't want to scare her off. You're like, I'm a huge science nerd, right? No, it doesn't work, right? Most of the energy, and I know we're almost out of time, is elastic, which doesn't change wavelength. A very small amount of light is inelastic, and that it's gained or lost energy. No photon is absorbed. It's not the absorbance of a photon and the emission of a photon. The same photon impinges upon a molecule's electric field, is diverted through mutual repulsion, but in that process, gained or lost energy. And the energy that it gains and loses actually comes from a vibrational band of the molecule. Most of you now have knitted eyebrows, like you're making a face, like, what is this nonsense? It is confusing as hell. And unfortunately, we don't have class Monday. So the next time I talk about this will be Wednesday, and I'm going to blow your collective minds talking about this. Be prepared. Don't come high. It'll make it worse. I hope you all have a good weekend. If you celebrate Easter, have a happy Easter. If you don't celebrate Easter, have a happy 3-day weekend. Stay safe. Don't do anything stupid. please.